for the linear algebra group projects, which I did by myself, I'm looking at electrical networks and applications of linear algebra in electrical networks. So what is an electrical network? Well, an electrical network would typically entail several different circuits with one or more voltage sources. So as you can see, we have our voltage source and several different types of resistors and a fuse here. And well, this is a very complex example of one. Let's simplify it to something like this, example B. So we have our two voltage sources and we have these three resistors. And all this is part of our electrical system that we will be figuring out using linear algebra. And to kind of find the current in the circuit, we need to use Kirchhoff's laws. So Kirchhoff's laws are linear equations that help explain how the circuit will behave. And the first one that we're going to talk about is Kirchhoff's current law. Kirchhoff's current law shows how when you have several different lines coming in, the currents actually add, which is linear. So here's two examples for Kirchhoff's law. As you can see, we have I1, I2, and I3, and you'll note that I1 and I2, the sum of which equals I3, because they all flow into the same line here. And if we have a situation like this down here, where I2 actually is leaving, we have I1 and I3, well, I3 is simply just going to simply equal I1 minus I2, which makes sense. It's kind of like water flowing through a pipe. You get a certain amount of water going this way and a certain amount of water going this way, which then brings us to voltage. Now, if you're familiar with Ohm's law, which is V equals I R, then you'll know that these circuits have three elements, which is voltage, current, and resistance. And so for the voltage law, once we have kind of figured out current, we can figure out some stuff like voltage and resistance. So the sum of any voltage in a current loop is 0, which is very important because if you were to have non-zero voltages, then a lot of these laws would not work. Which then brings us to here. So how do we solve for this? Well, this brings us to the third law, the final law, where V equals IR, where V in this case is actually E, which is our power source voltage. So we know all this, and we can kind of rewrite these two loops. So we have one loop here and one loop here. And we can rewrite these loops where our 5-volt loop, which is the top loop, is equal to 20I2, which is 20 ohms, with I2, we don't know what I is, and 10 ohms in I3. So we have a loop going this way. And then for our second loop, we have 10 volts equals negative 10I3 plus 10I1. And so we have I1, I2, I3. I3 is going this way, I1 is going this way. So we're going to have negative 10 for the I3 because it's leaving this loop, sort of. It's going the opposite direction that the loop is wanting to go. And we're going to have positive 10 I1 because we have 10 ohms for I1. And so, as you can see, you can rewrite this using our initial equation showing, you know, that the sum of all this is going to equal 0 because these all cancel out. They, I1 plus I2 equals I3, so I1 plus I2 minus I3 in this case equals 0. So, if we plug it into this matrix, and this is an augmented matrix, so that way we can solve. Once we take the reduced row echelon form, it actually gives us the proper current ratings for each one. So I1 is 3.5 amps, I2 is negative 1 amps, and I3 is 2.5 amps. That's pretty much it for the video, but that's just how linear algebra can be applied to circuit networks.